So we started recording. Few things before we start. We have few slides to finish in the advanced topics one, but few things. First, the homework number 2 solution is already uploaded into Brightspace. The table, as I mentioned in the announcements on the course website, has all the groups and the projects. We have 18 projects. So, I mean, not 18 different projects. I mean, because we allow projects to be repeated. And don't worry about repeated projects, because I will not compare groups to each other, basically. I'll just look to each group alone, taking into account the work, the number of people, and all of that stuff. And especially that with the same project, you can do many different implementations, so things will be perfect, fine. Another thing that is quite important regarding the grading, whether the grade for a lab or a homework assignment, don't take these grades blindly based on the grade distribution in the syllabus, because at the end, after we finish the final exam and submit the projects, I will curve everything. So your absolute grade is not important. It's actually how you relate to the other people. Okay, I don't know whether you assume that this is a good thing or a bad thing, but you know, most probably it will be a good thing. And given the grades that I found for the lab 1, actually the grades are pretty bad. Well, not bad, but let's say average, which is okay, because this means that I'm not going to use your absolute grade. I will just, the highest grade will be the A, and then I will go like this. So don't worry about the grades. Concentrate on the learning experience for now. Okay, this is one thing. Also, if you go to the discussion forums, you will find now we have 2 forums. One for the technical topics that we are discussing here. So we have a topic for everything. And another forum called the projects. And these are numbered from 1 to 18 based on your project number in the table. And this will be the way of communication between each group and myself. If you implemented something and you need my opinion, if you don't know how to implement something and you need my opinion, you know, these things. This will be our way of answering that. Any questions about this before we go to the more interesting stuff? Okay, we will do 3 things today. First, we will finish the few slides we have left in the advanced topics 1. But before we start advanced topics 2, I thought of sharing with you some slides. They are also on the course website about CUDA tools and some important switches in NVCC and all of that stuff. Some CUDA tools, some of you have used already when they started their projects or as part of the lab, like NVProf and all of that stuff. We'll talk about them here, but also because we will be giving a small piece of information is that NVProf will be deprecated and retired starting from after Ampere, basically. So we're talking about Lovelace and up. However, they are still working, so you can still use them here in the project that you have or in the labs. So we'll be talking about them also. And then we'll give one slide link to Nsight, which is the one that will be more, I don't know why it's fogging today more than usual. Okay, that's better. Nsight is all the ones that will be supported from now on with NVIDIA. Okay, and then after we finish the quick tour in the CUDA tools, we'll start CUDA Advanced Topics Part 2. Asynchronous execution. By the end of last lecture, I asked you what does the word asynchronous mean, and all of you got it right, which means it's blocking, basically, which means whoever calls this API will be blocked until it's done, and then it is coming back. It is causing some confusion in CUDA, because some APIs are blocking, some others are non-blocking. How do we deal with that? And being non-blocking especially is a little bit tricky when it comes to error handling. Until now, in the labs, we don't ask you for error handling. If we try to trick you and enter some wrong inputs, how will your program? Because I mean, so far your programs do not handle correct inputs correctly. So we don't really need to exercise them with the wrong inputs. But just in case things, when they are non-blocking, kernel launch, for example, it's non-blocking. So how will you know that it was correct? So it's very important to know what is blocking, what is non-blocking. So asynchronous, it means it returns to host right away and does not wait for the device, which is good, because then the host can start doing something else and you have another level of parallelism, like the kernel launch. Even though CUDA memcopy is blocking, and this is a different story. We will see in the advanced topics too some CUDA memcopies that are non-blocking, but they require some special handlings before using them. So the asynchronous are the kernel launch, memory copies between two addressees to the same device. Remember, in CUDA memcopy, you can have from device to device. That will be non-blocking. But if you go from host to device or back, it will be blocked. Memory copies from host to device for memory block of 64K or less, because this is very small amount relatively. So the CUDA runtime can buffer them and return the control directly to the host, and then it will just send it. But usually we send way more than this, because for something to be really worth of running on GPUs, the problem size really is quite big. Memory copies performed by functions that are suffixed with the word async. This will be in our advanced topics. We haven't discussed this yet. Anything else, or from what we have seen until now, they are blocked. Some CUDA API calls and all kernel launch are asynchronous with respect to the host. This means error reporting is also asynchronous. This is the thing. So basically, CUDA memcopy async, this will return to you right away. But in order to use this, we need some special handling. Why? Why do you think we can just blindly use this instead of the traditional CUDA memcopy?
So we need to know when it's finished.
Why?
Because we need to make sure the things the copy is ended.
That is important. This is a very good point. But this is related to another important point, which is you don't want, while you are copying from host to device, that this data is paged out. Remember, virtual memory, so things go back and forth. This will be pretty chaotic if while you are copying, the operating system starts to page out something, or you want to copy something that has already been paged out. So in that case, in order to even start, you need to wait until. So we need to tell the OS, do not page out what we are gonna. This is what I meant by we need to prepare for using this. Kernel is non-blocking. Any kernel is non-blocking. This is why you can do something here before you put a memcopy back. Then you have some kind of freedom to do something here until everything is done. Okay. This is streams, and we'll talk about streams shortly, because this is one of the things that will boost the performance of your code a lot if you use it quite well. Streams. First, let's think a little bit about something that I am sure you didn't think about unless I go to the class. You send something to the host, the device, block, and then you launch a kernel, non-blocking. So this means it will come right away to the next statement. That next statement until now for all the code that we have done is CUDA memcopy back the results. Okay. who told you that the kernel is done before you start bringing stuff back from the memory? I think you asked this few lectures ago. Because then you can start working or bringing the stuff back without the kernel finished, because the kernel is non-blocking, so you don't know. Well, you can say that you can have some kind of synchronization, and we'll see some APIs to synchronize. Or you can be doing some polling. Are you done? Not yet. So do something else. And then are you done? Not. And then once it's done, you bring the stuff back. Both of these things are very inefficient when it comes to performance. You are just wasting your time. The best way, in order to not to lose performance in that case, is to do something very simple. Can you think about? Huh?
Use another queue to because that's keep the order.
Exactly. So the best thing is to do nothing. Why? And I will come to the interrupt point later. Under the hood, when the host is talking to the device, the CUDA runtime will establish a queue of work. So any command that you send to the host will be put into that queue, and the device will be executing them in a queue fashion, which means in order, which means first in, first out. So even though you start the CUDA mem copy back right away, it will not really, it is after the CUDA launch in the queue. So in that case, it will be executed only by the host, by the device after the kernel is done. So if you do nothing, your work is still correct. Because if it's not like this, all your lab one submission would have been wrong, right? So that is one important thing. Now, when it comes to interrupts, how many of you have heard of interrupts? Okay, exceptions. What is the difference between exception and interrupt? This is something not exactly related to GPU per se, but for the whole computer system. Interrupt is a hardware thing. Interrupt, it means it will interrupt the machine while it is executing your code, no matter whether this code is on the device or a host, because there is an external event that requires the attention of the operating system. So what will happen when this interrupt comes is that it will stop everything related to user. It will switch to kernel mode. The operating system will take over to do whatever it has to do for that interrupt. Okay. Usually, this is coming from something like a hardware thing. For example, paper jam in your printer. Always when you get this screen of paper jam, this is really interrupting anything you like. You'll find it just in front of you, like the advertisement you get when you go to some websites, okay, that tells you to subscribe and all of this, nonsense. So these are some kinds of this, but there are also some interrupts that happens in a standard way. The timer inside your machine interrupts the processor 18 times per second. This is a standard, and you cannot mess out with this. Another thing, if you look at the pins of a processor or the pads, there are very few ones for the interrupts. What if more than these pins of interrupts happens? What if 6 interrupts came at the same time? Paper jam, something came from the Ethernet card, because the stuff that comes from the internet, you have to read them quickly, otherwise the buffer will be filled up and you will lose data. And then you have the timer and so on. What will happen in that case? First of all, anything related to hardware has higher priority than software when it comes to interrupting the processor. Okay. There is a chip on the motherboard. That chip basically receives all the interrupts that are coming from all the system, prioritize them, and then send them to the processor through these pins one by one. It's called the PIC, Programmable Interrupt Controller. Programmable because if you are a geek, you can change the settings of these things and change the priority, or even stop some interrupts. If you stop the interrupts coming from pressing the keys of the keyboard, then the keyboard will be non-responsive, for example. Okay. This is one of the things. The GPU is considered an I/O device, similar to a disk or keyboard and all of that stuff. So the interrupt it causes happens when there is a hardware problem only. Okay. Now, exception is really a bug in your code. Simply speaking, if you are dividing by zero, then dividing 0 by 0, all of these nice stuff are exceptions. So it is because of us. And if this happens, also the operating system has to take over to kill your process, for example, segmentation fault and all of that stuff. But if this happens at the same time as an interrupt has higher priority. Okay. All right, now back to this. So the word stream is the queue that we mentioned that the CUDA runtime will make between the host and device, so that when you put the commands inside that queue, the device will do it in order. But as you can see, this is a plural. So it means that you can have more than one queue. What is the importance or the advantage of having more than one queue besides making our code more complicated? One important thing is the device will execute things in one queue or one stream in order. But if it receives several commands from several different streams, it can execute them in parallel. So how do we make use of this? If you put a CUDA mem copy in one stream and then a kernel in another stream, then basically the computation will happen at the same time as moving the data back and forth, because they are in two different streams. So in that case, you are hiding the latency of the communication. We said before, when something is slow, either you speed it up or you hide it. Hide it, it means you are doing something useful at the same time of doing the slow part. So here you are putting a kernel launch in one stream, a CUDA mem copy in another stream. So the communication happens at the same time as the kernel launch. You can put two kernels in two different streams. In that case, these two kernels will be executed in parallel. Of course, all of this, assuming we have enough resources to execute all of this. You can put two CUDA mem copies in two different streams. So in that case, you may be moving data in one direction and data in another direction, for example. Okay. So streams are our way of executing several things in parallel at the GPU. Okay. Of course, it is your responsibility as a programmer to ensure that the things that are executing in parallel can really be executed in parallel. So you don't have any error in the logic and so on. So you cannot put the CUDA mem copy that will bring back a result of the kernel in a different stream than the kernel itself, because in that case, it can really start before the kernel finishes and you'll get the wrong results. Okay. Yes?
We put two mem copies, two independent mem class copies in two different streams at the same time.
In
two different streams at the same time. How are they split over the bus? Like, is that done automatically, or is it half of the?
No, it's not half. It's a CUDA runtime will look at how much you want, because at the end, PCI Express, for example, is lanes. And depending on how many you want to bring based on the CUDA mem copy, the CUDA runtime will see, okay, I can give you only 25%, and for the other 75% because it's sending more. So it depends on how much you want to send. If one of them is taking all of it, then it will be sequentialized. You don't have resources.
And the runtime decides this on its own, or can we specify? The runtime does this allocation on its own?
Oh, yes. Yeah, you don't have control over this. And there is a reason, by the way, you don't have control over this. Actually, two reasons. First, it will make the hardware, the software way more complicated. And the second, you will not. The second thing is, related to the first, you will not be able to test this in the labs here, because then if several persons for the same CUDA cluster is trying to do something different, and this is a problem. Well, the second thing is, across this communication, the runtime is sending some other stuff related to control and signaling that is outside of your control. Remember that beside all of this, we never mentioned how the kernel itself will go and how setting the stage and all of that stuff there. So all of this happens there. So you cannot, as a programmer, have full control of the PCI Express or NVLink in that case. So streams, to summarize what you just said, a sequence of operations that execute on the device in the order in which they are issued by the host. Operations in different streams can be interleaved, and when possible, they can even run concurrently. You know, of course, the difference between interleaved and concurrent. Concurrent at the same time, interleaved a little bit of this and then that, and then back and forth. A stream can be a sequence of kernel launches, host device memory copies, anything that you tell the device to do can be done there. Can have several open streams to the same device as at once, depends on how much. But of course, although the upper bound is a very large number, the number of streams, but after a handful of streams, you will stop seeing a lot of performance because the GPU itself may run out of resources. So if they run out of resources, things will be serialized anyway. So you will not really gain anything except paying for the extra work of setting the streams and all that stuff. This needs GPUs with concurrent transfer and execution capability, which is anything after Kepler. And Kepler itself is so old that it will be deprecated with the next CUDA. So all the GPUs, as long as you got your GPU in the last 5 years, it will support this. Potential performance improvement means potential, it's not guaranteed. So for example, if you do a lot of effort in this course, you can potentially get an A. Potentially here, it means that there is a probability. It can be a good probability, but it's not guaranteed. You can overlap transfer and computation. This you cannot have in your grade. You cannot overlap in A and B, for example. It doesn't make sense. This is how it looks like. If you don't do anything, which is what we have been doing until now, everything will go to stream built by default by the CUDA runtime called stream number 0. Okay, this is what happens. The host will be putting the elements, so CUDA main copy followed by kernel launch, followed by CUDA main copy back. The device will be executing them in order. This is why everything was working correctly so far, even though some are blocking, some are non-blocking. Okay, so this is what we have been doing in that code, which is our default so far. Do you remember, by the way, what was the third arguments when launching a kernel? We learned something that has a third. Exactly, the dynamic shared memory is the third. The streams will be the fourth now. So we will, in the code above, from the perspective of the device, all 3 operations are issued to the same stream and will execute in that order. From the perspective of the host, the CPU, data transfers are blocking. You are blocked. Once you reach here, you are sure that the data has moved. And then here, it will return right away. And then you start doing this. And this is blocking. And it will not return you from the block until the kernel finishes and this comes, which means you will be blocked for a long time. This is why it will be good if you put something here in the middle, doing something else before. Do you think it would be beneficial if we put something here? Yes or no? Well, beneficial here, it means for the overall performance of the program.
So if you put something which can be done by host, then it is beneficial.
As long as this something will not take a long time that you will not start the CUDA mem copy back.
Yeah.
So you have to be careful about this. Okay, so if you put something here, that's fine. Unless you put something here that is actually non-blocking also. Start the threads and some threads will do something else or whatever. Okay. Any questions? Okay. Now, how to create streams? Non-default streams. First, you need to declare them. Declare here, it means you have to give them a name. It's like int x, so you have to declare them. Once you give them a name, you have to tell the runtime, CUDA runtime, that, oh, I created the threads with that name. So this means create. So just the name, and then creating the streams, then use it, and then once you are no longer in need for it, you destroy it. Why you need to destroy it? I mean, your program will not be long if you never destroy it. But this means if you have a lot of them, you are pushing the CUDA runtime to keep track of more things, slowing down the CUDA runtime a little bit. Okay. So declaring, this is the type of the stream defined in CUDA.h. So CUDA uppercase here, stream type, you call it anything, stream one, variable name. And then create, CUDA stream create, and you give a pointer for that string. Okay. Now, if you want to issue a kernel to that new stream, then increment, sorry, whatever the kernel name, and then the fourth element is the stream number. This will be the fourth argument for the kernel launch. If you don't want to have, it has to be the fourth. So if you don't have dynamic shared memory thing, just put a 0, but because you cannot put 3, I mean, it will be. Now, how to make even a better use of this? Once you have this kind of non-default stream, you can use asynchronous CUDA mem copy also, freeing the host from even more stuff, which has exactly the same arguments as the CUDA mem copy, with the exception is that we have the last argument to be the stream that you have created and the word async here. Okay, question?
No.
Oh. You cannot use CUDA mem copy with the default stream, so it has to be with one of the streams that you created here. Okay. Any questions? All operations to non-default stream are non-blocking now. We have now CUDA mem copy async. We have the kernel launch, which is non-blocking by default. So that's mostly what we need to do, right? Sometimes you need to synchronize, though. If everything is non-blocking, sometimes as the host, you need to know what is the situation with the device. Is the device done with this part or that part? Because maybe you need the data that is calculated there to continue something that you are doing here, right? So how to do that? How to synchronize with the device? There are two ways of synchronizing the device, and these two ways are implemented in CUDA with 3 APIs. The two ways, one of them is blocking you. So you will be blocked until whatever there is done. The other is not blocking you. It will just tell you it has done or it has not done. This will be the polling thing. Sometimes you need it, but busy waiting is not the best way. But sometimes you may just need to poll, and then if it says I'm not done, you do go something else and then come back. So 3 things. CUDA device synchronize. This will block you. It will block the host until everything is done at the device. Okay. CUDA stream synchronize. This will block you until that specific stream or the tasks in that stream are done. Here, everything must be done from all the streams. Here, that stream only has to be done. In both of these cases, you are blocked at the host. Here, you query only. Query, it means it will return CUDA success or not, which means that that stream is done or not. Okay. One important thing I want from you to realize in this CUDA, which is related to what will happen at the end or after this class, not this specific class, I mean, this course, basically, is that CUDA as a language evolves almost every 6 months. So I had sometimes to change many things in the material here. So don't take what we are studying here and assume it will be with us forever. So maybe every year or something, go to the documentation of the link of this documentation is on the course website and check what happens in CUDA. CUDA will be with us for at least a decade. It will not disappear, but it may change, it may evolve. At some point, you will find that CUDA will start using or outsourcing to AMD GPUs, for example, or Intel, and so on. But after CUDA, we will also look at OpenACC, and then we will look at how bad OpenCL is. So we'll not go deep into OpenCL. I'll just show you some stuff that are more than enough to show you how bad that language is. And there is a fourth thing that also outsourced to GPU, which is OpenMP itself, but we will not actually study it here. There are some other languages, of course, but those are the most powerful. Anything else is at higher level than this. I mean, OpenACC is even higher level than this, but CUDA is the most mature so far. So the amount of overlap of execution between two streams depends on that device has to support overlap transfer and kernel execution from compute capability 1.1, so it's everybody is there. Supports concurrent kernel execution available from 2.x. Now we are at 8.x, so everybody is there. But you have to be careful. Even at Ampere GPU, at most 32 kernels can execute at the same time. And if you are doing this for the lab, remember that many will be running on the GPU as you. So 32 overall. Device supports concurrent data transfer. So either multiple kernels or kernel and communication or two communication. The GPU supports all of this starting from 2.x. Okay. And it also, this depends on the order on which commands are issued in each stream. What do we mean by this? If the communication is really, both of these communications are going to the same direction, they will require more resources if they are going on different directions, because the PCI itself is lanes and each one is in one direction. NVLink is a little bit faster. Okay. And the way I put the streams in the flow of this course is that today we'll start looking at multi-GPU systems. Multi-GPU systems is not hard to use, but it is hard to program. This is why NVIDIA is a bit slow in introducing the subsequent versions of their NVLink, because the programmers who are writing games, for example, they found it much easier to write their game for a bulky, big GPU than to multiple GPUs. Because in multiple GPUs, you need to synchronize. You don't want the sound to come before whatever these things. This is much harder to do when you have things connected with that. So people are not buying NVLink systems as fast as the company hopes, because people like to buy only one bulky GPU. But for high performance computing, multi-GPU is the norm. If you look at the top 500, we'll see actually, we're coming to this. Okay, so using streams to overlap device execution with data transfer. The device must be capable of concurrent copy and execution. Copy means CUDA mem copy, and execution is kernel launch. The kernel execution and the data transfer to be overlapped must both occur in different non-default streams. So once you started using streams, forget about stream number 0. Everything will be in different streams. The host memory, and this is the most important now, the host memory involved in the data transfer, okay, must be pinned. This is what we mentioned like 15 minutes ago. You don't want the data to start to be paging out while you are trying to transfer. So you have to pin them in memory, telling the operating system not paging it out. There is a good and bad things about that. The good thing is that you can use non-blocking copy and overlap transfer and all of that stuff. What is bad, if you pin more pages into the memory, this means the operating system has only much less memory to keep, to keep paging in and out, which means page faults may increase. Page faults will bring your performance down at the end. So you have to be quite careful about this. Now you know why you are not yet there in automating writing code. Why they still need programmer, because you have to, there are some trial and errors here when it comes to this, turning some knobs before finding out what is going on. Okay, so let's see a bit of code here. Okay. We have CUDA name copy async. Copy from here to here, that number of bytes. CUDA from host to device, and stream I. Stream I, because now we have an array of streams. This is a for loop. So every element of that array is just a stream that we have declared somewhere there. And then you will call the kernel by putting the different stream in here, and then you could have him copy back the stuff. This is how we can overlap. This means every iteration is really one stream. Okay. How many of them? It's up to you. I mean, the upper bound is very high, but as I said, the performance will not go linear. In most of the cases, it will be sublinear, and then it will flatten. If you keep continuing, it may go down a little bit because you will be paying for those streams without really making use of all of them. They will be serialized. Okay. So streams are a good way to overlap this execution, data transfer, and all of that stuff, assuming we have enough resources. I hope that you will not confuse kernels from threads from streams. Okay. The lab is supposed to be submitted next week, right? So now you can use streams. If I don't forget what the lab was about, but maybe streams can be. Hint pages. Okay, in order to be able to pin something, you must not use malloc. Okay. One important thing regarding memory allocation, just in case you forgot. You know that the dynamic allocation at the host has its playground in the heap. Anytime you use malloc, it will be in the heap. Okay, this is one thing. Malloc is not the most efficient way for multi-threaded applications. Think about several, it is reentrant and thread safe, but it's not the most efficient thing. If several threads in parallel in the host and each one is doing malloc, this is not the best way. This will be better. And there are actually, there are many dynamic memory allocators available. They are a dime 100 basically. And especially that there are some very good ones for the multi-threaded application. One important thing, whenever you call dynamic allocation, do you think it is a system call, yes or no? It's very important to know this. Anytime you call a dynamic memory allocator, it is a system call. Okay, before I comment on this, if I show you two dynamic memory allocators, how do you say, or how do you tell that this is better than that? What is your measure of success? They will both allocate from the heap. Okay, so the speed of the allocation, this is one thing. Usually they measure it as the throughput. So they test it by having a loop of many allocations and they see how many is the time and all of this. So this is one, but it's not the only measure of success. There is something else very important.
How properly it is allocating, like
How?
How efficiently it is allocating. It should not
Define
go
efficiently.
it should not go and just allocate in a memory from middle or somewhere in between, so that there will be less waste of space.
Okay, you have the right idea, but a wrong explanation. Because sometimes it would be good if you get something from the middle, and I will tell you why. And it is related to what you said. Not every memory allocation is a system call. Why? Unlike the stack, from the bottom of the stack to the top of the stack, we know that the whole memory is filled up. But from the bottom of the heap to the top of the heap, we may find holes. Why? Because you can allocate, and then free something in the middle. Okay. So the dynamic memory allocators, all of them, they are trying to keep track of these holes so that if you ask for a dynamic memory, it will try to service you from these holes. And if it can, then it will not call the operating system. So it's not all the calls to malloc or whatever. So, and this affects, of course, the speed, because if it calls it calls only the operating system when it needs more heat. So all these holes are not. And then why I said there are hundreds of them, because if you have several holes, which one will it pick? It can be first encountered one that is big enough. It can be, this is called the first fit. It can be the best fit, which is the smallest one that is, and it can, people even tried something very nice and crazy. It's called the worst fit. What is the worst fit? It's the biggest one, actually. Why? Because once you take part of it, the rest can be big enough to be useful with something else. Okay. So many of these, and when you have a multi-threaded application, things are becoming even more interesting, because they are all, remember, multi-threaded, it means they are sharing the memory, so they all see the same heap. Okay. All right. So if you allocate with malloc, the pages by default can be paged out for that data. But if you call with this or that, they are doing roughly the same thing. I mean, the reason is when they upgraded the CUDA, they kept the old one for backward compatibility. But basically, CUDA malloc host, so it will be similar to the word malloc. Okay, so accessible by device, and this will start another very important advanced topics shortly, is that you are allocating in the heap of the host, but the device can access it. We'll see now how this happens. Until now, our relationship with memories is that the host has its memory, the device has its memory, and we keep moving stuff back and forth. We'll see how we can do otherwise. With those, unlike malloc, what you allocate here cannot be paged out. So in that case, you can use them with the CUDA. Enables highest memory performance because they cannot page it out, so you can use the I think. Of course, if you use these instead of CUDA free that we used with, you need to use CUDA free host, because CUDA free will free from the device. This will free from the host. Taking into account this, if too much 10 pages, overall system performance may greatly suffer. So the advantage that you'll get from the GPU will be canceled by the slowdown. All right. Okay, I want for you to see this. The CUDA host alloc. The first two arguments is similar to the CUDA malloc. Basically, is a pointer to a pointer, the one that and the size that you want. What is quite important is the third, the flags. With the customs of NVIDIA, we have very long flags, as you can see, that they can put for some reason, they all start with CUDA host alloc. So what was wrong with saying just the old portable map? For some, they have to put the whole thing. And especially that these are not really, they are constants. So in CUDA.h, they are really numbers, 0, 1, 2, 3, 4 at the end. So CUDA host alloc will cause this to act as the CUDA malloc host, the previous ones. You remember, we said the dynamic memory allocators have different implementations, best fit, worst fit. So this will make it compatible with the old one that was there. CUDA host alloc portable, this is important flag for us. The memory returned by this code will be considered as pinned memory by all CUDA contexts, not just the one performing the allocation. Have you heard the word CUDA context before? Anybody heard the word CUDA context? Kernel launch. So if we have multi-threaded, every thread's launched at the kernel, they will all see this. It's called different context here. CUDA host alloc mapped. This is also a very important flag for us. Maps the allocation into the CUDA address space. So it's not only in the host, but also in the device. Remember something. it is mapping it to the address space, but it is not using any storage from the device memory. It's only mapped. You remember the addresses in the memory of the device was 64-bit if you go back few lectures ago, and we said that only 40 bits are used for that whole thing. So for sure, the storage you have in the global memory is much less than 2 to the 40. But that address space will have part of it, the virtual address space part of it will have that thing mapped to it, which means under the hood, or it means for us as a programmer, that while you are at the device in the kernel, you can access something from the host without copying the data. Zero copy. Okay. However, you cannot use the pointer that is at the host right away. So there is CUDA host to get device pointer. To get a pointer that you can use now, the host has a pointer, the device has a pointer. Both pointers are really pointing to that same thing that has been allocated by CUDA host alloc. Okay, what is the advantage of this? Let's think a little bit. Speed-wise, accessing something from the host while you are at the device is much slower than even accessing the global memory, because it involves accessing memory and then going through the communication and getting the data. So it comes really from the system memory to the level 2 cache right away in the device. Okay, so we didn't really get that. Maybe one of the advantages you may think is we didn't use a lot of things, a lot of storage from the global memory, because it is still much smaller than the system memory, 32 gig at most, even for the state of the art. So it's not yet what we want. Another thing is people are using this technique if you need a piece of data very rarely. So really you don't need to copy it and then so just you access it once. Maybe you need just one number or few numbers or something, and that's it. So this is what we use. The third or the fourth one, so this you will not need to use. These two are important. That you will not need to use also, because this affects the CPU, which is CUDA host write combine allocates the memory as a write combine. It will try to coalesce the memory that is in the host, just in case when you try to copy them, they will can be combined quickly. But if it put them that way in the host, it will make the CPUs themselves accessing their own data much slower. So this is not the best way to use it, especially that it is now getting out of fashion. So basically, I will not find many systems are doing this. This is not important. This is not important. These two are quite important for us. Any questions about this? Oops. Some reason. Okay. Here we are giving more details about this pointer thing. You use the third flag from the previous slide to CUDA host alloc. So this means now that the data that was dynamically allocated at the host heap has two characteristics. One, cannot be paged out. Two, can be accessed by the device. But before the device can access it, you need to get a pointer for you to be able to access that thing. Okay, remember, this is the virtual memory for the host, virtual memory, virtual address space, sorry, for the host, virtual address space for the device. Each one needs its own memory, even though you are accessing the same thing. This is very similar, by the way, to the shared libraries. If you are running several programs on your multi-core, on your laptop, and several programs are using the same library, some graphics library, for example, that same library will be in the physical memory, but it will be mapped to several virtual address space by several programs. This is very similar, but instead of being several processes, it will be the host and the device. Here you need to have CUDA host get device pointer. This is the pointer of the device of the host, the one that you got with the CUDA malloc. And then this is a pointer at the device that you declare and you pass the pointer to it. This flag is always 0 and it is left for future use. Let's concentrate on the third argument, Z. And it has been 0 for the last 3 years. I'm not sure what future upgrade they have been waiting for. I think this will be deprecated before they decide to. And I expect that this will be deprecated in a year or two. And I will tell you why today as we proceed. But for now, it's still there. So it's now accessing host memory. Once you have this, then you can use this pointer as the kernel to access anything from the host right away without copying anything. This is why they call it zero copy mechanism. Accessing the host memory from the device without explicitly copy is called zero copy mechanism. You cannot do this with a lot of data, as we said, because we said its access time is worse than global memory. And also, it requires pinned memory there. And you don't want to have a lot of pinned data there. Okay. So the steps, because we said a lot of details here, the steps for the zero copy. You allocate in the host with CUDA host alloc. Use the flag CUDA host alloc mapped, which was the third flag there. And then use CUDA get device pointer to get the pointer for the kernel. And then use that pointer in your kernel as if it is in the global memory. The good thing here is if you use a piece of data from the host, but you keep using it a lot, only the first one will be slow because these things will be cached in the level 2 cache in the device. So this is good. Any questions? Are you sure you don't have any question here? Okay, I will ask you a question. And yes, sir. First, the memory, the global memory is still restricted in size, 32 gig, or so it's always on average smaller than the system memory. This is one thing. And the second thing is, because it's like that, you don't want it to bring something that is already copied from here and here. This is wasted resources. And if you are going to use this data rarely, then you don't want to pay for the transfer and back and all of that stuff. So this is another thing. A scenario that may be useful for some programs is that if this data that you are using during kernel is updated frequently by the host for some application. Because if you are using the traditional CUDA copy, then you have to bring it each time it is updated. Okay. But that was not the question I expected. There is something else in here. Okay, I will ask this question. What if the device tries to update that data? I write to it. Now we have a coherence problem. There is level 2 cache in the device that has a copy of the data that is in the host memory. We are facing something because that data that is there may be in a cache of one of the multi-core there also. Then you have a coherence across devices. So they are doing something ingenious here. Can you guess? But when I say ingenious, doesn't mean necessarily it is complicated. Sometimes the ingenious ideas are pretty simple. What is the simplest thing that you can do in that situation? What?
Keep 2 copies in the host memory itself.
Do what?
Keep 2 copies.
Keep 2 copies. Well, then with the, I mean, the
In
file.
the host memory, not in the CPU memory.
Okay, but then you have to keep track now 2 things of the same name, right? Well, the simplest thing you can do for something like this is to do nothing. It's the problem of you as a programmer. Why do you want to update something that is, until very, very recently, coherence was not supported across devices. I said very, very recently, until we reach advanced part 2. Okay. Okay, sorry for the small font here, but I want to put the whole code in one slide so we can look at it. Okay, let's start with the main function. We have a bunch of pointers here. CUDA host alloc. So we are allocating in the host several things for A, B, and C. Okay. And then those are arrays. We will load them with some numbers. And then CUDA host to get device pointers. We are getting 3 other pointers for the device, A, B, and C. We are passing the pointer to a pointer, as well as the pointer for the host. You know, the name of the array is a pointer to it. The third is always 0. Now that those 3 pointers can be passed into the kernel right away. So now there, they can just use div A of 0, of 1 or 2 as if they are just traditional arrays, and they will be actually accessing and modifying the arrays in the host. Okay. But as I said, if you write to it, ensure that nobody there is writing to it. Otherwise, you'll have a coherence that is not supported. Okay. After you are done, you can just free the host, free them with this, not the traditional free. Remember, because these are not paged out. And here is the kernel itself. So in the kernel, they are using the A, B, and C as if they are traditional things, which are these pointers. So they're used as if they are traditional arrays. And here, you may think it is just very similar to a code that we have seen with the traditional CUDA mem copy and all of that stuff. But actually, here you are accessing the memory of the host. Any questions? Yes, sir.
You are
Oh, okay. So first come, first serve. Then. Yes.
Why isn't the memory paged out?
What is the memory?
Why isn't the memory paged out? Is it because the CUDA runtime allocates the memory?
CUDA host alloc, by definition, allocates data that cannot be paged out. This is why we are using this. We are not using malloc.
No, I'm asking why does POS?
Why does not? Because it's getting a hint from you that I need this data, not to go out. It's like there are some very low APIs in C, for example, that you say that I want this data to be non-cacheable, for example. I don't want this data to be put in cache. So sometimes, you know, you need to give some hints. You have a question.
in the kernel code, we are doing assignment to C.
Yes. But the host is not doing anything to C. So we don't have any problems.
But there are chances in host it is in the
Oh,
cache.
yes, yes. If there is if something is writing to C at the same time, yes, you'll have a coherence problem and the data will be non-deterministic. But what is the advantage of this is that there is no CUDA mem copy back or anything, at least from a programming point of view.
But it's gonna be anyway very slow, right?
It is going to be very slow to some extent, but not as slow as you think, because you will get with the first element a cache miss. So the level 2 cache will start getting several elements at the same time. And the cache blocks in GPUs, level 2 cache blocks are much bigger than the cache blocks in CPU. Cache blocks in CPUs in traditional multi-core are mostly 64 bytes in the current multi-core. For GPUs, we are talking 128, 256, much bigger. Bits, sorry, not bytes.
For reading, right, caching can help, but writing you cannot avoid the time problem, right? Because we are assigning things to C.
Of course, yeah, it will go back. Yeah, that's true. But is it much worse than copying the things back or not?
Yeah, that only I was about to ask. Like doing it such way, or I'm adding C to my GPU memory, and then after this kernel, I'm copying it. So what will be the one?
Most probably, depending on how many elements in C, there will be a small size where this is better until there is some point where copying the whole thing is much better. So if those arrays are quite big, then you better move them.
And also a question, does that make us to ping the host memory too much? Because if we want to use GPU, the size of array should be very big.
Yes, this is one of the, this is why I said that usually you use these things if those are small. For example, you want to read only very small numbers and then you will be using them a lot. That is the only thing. But if you want really to do the big problem size, as you said, you better bring them basically. But now we learned a way that even if they are really huge, you can bring part of it, do some work, and at the same time you are sending something back with streams and all of that stuff. So if the CPU program requires a lot of memory, then 10 pages is not, depending on what you are doing in the host. I know that for this course, we are concentrating on GPUs. So we are making an implicit assumption that the host is doing nothing while the GPU is, but in real situations, the host is doing a lot of things. So we have to take this, into account. Okay, that finishes the first part of the advanced topics. Just a small thing, because we have seen a lot of details so far. So this, I put this thing to summarize. When you program for the GPU, you need to pay attention to several bottlenecks: branch divergence, global memory latency, global memory bandwidth. All of these, you can get them, or most of them, with the CUDA get device properties that we shared memory bank conflict, the communication back and forth, limited resources. We have seen this, and the limited resources is more severe than the multi-core because a block needs to get all the resources beforehand. Otherwise, it will not be assigned. So this can delay you a lot. And then, in order to cope with this, we have learned many things now. Same control flow, paying close attention to if else, if at all, tiling, coalescing, loop unrolling, increasing or decreasing thread granularity, thread one resources for the other. This is quite important. If you look at the top 500 supercomputers, and we'll see a slide shortly about the top 10. Why the top 10? Because first, I don't want to waste time and put 500 machines on slides. But the first top 10 have 38% of the total performance of all the 500. This is one thing. Second thing, 6 out of the 10 are based on NVIDIA GPUs. So basically, it's doing a lot of work. But now you will find something quite interesting in this list. The first, if you look at the benchmark they are using to get the top 500, it's called the LIMPAC. The LIMPAC is basically this. It's very simple. It is solving a set of linear equations with some of number of unknowns. Okay. So this is a matrix, this is the unknowns, and this is the constant there. So this is a dense matrix operation. So what is quite important is how fast the GPUs can do a lot of work. So you will find for every supercomputer 2 numbers, Rmax and Rpeak. Rpeak is the theoretical upper bound. They just look at the G-flops of every GPU and multi-core and multiply it by the number of GPUs and multi-core. So it assumes 0 communication, 100% cache hits, and all of that stuff. And then there is Rmax, which is the maximum thing that you receive really in the machine. You will find that for this dense matrix thing, the impact, the machines are, especially for the top 10, they reach 80+% of the Rpeak. Now, when they run it or they test those machines, high performance coefficient something. This is sparse matrix operation. Once you do this, you will find that those machines are reaching only 3% of the peak. The best machine in the old 500 reaches 5.6% of their peak. What is the problem? One was dense and the other was sparse. The problem is when you have a dense matrix, the operations are way more important and we have very little communication. With the sparse matrices, communication and the interconnect is critical. And because it is very expensive, it brings the whole thing down. That is the whole story. And there was actually a very nice talk by the guy who made the top 500. It started in 1993. I can put that link somewhere in an announcement or in the course website, so you can see this. Okay, let me move to the quickly before we move to CUDA Advanced 2. I just need to make a quick. How many of you? Why it's not very happy? I just changed the slide. Okay. So how many of you have used any tools beside NVCC? Raise your hand. Okay. How many of you have used NVCC? Of course, how the hell did you submit lab 1? Okay, first, if you go to one of the CUDA clusters and type this, the system management interface, -Q, it will query the GPU attached to it. It will tell you how many GPUs and all of that. So it does something similar to CUDA get device properties, even though the CUDA get device properties gives you more information, but this is just if you want to quickly. Here you need to know the version. The last one I have, or the highest one I have seen was 10.2. So before you run anything, use the 10.2. Well, the latest one in reality is 12 something. They haven't installed it yet. Okay, but you can just LVCC and the version, it will tell you the version that we have seen. It has been there for a while, I mean, 2019. And then there are 2 versions after it. It looks like the NVIDIA folks had a lot of time during the pandemic to do 2 versions of the CUDA since they are working from home, all of them. So, okay, the NVCC. I put the links because they keep updating this thing almost every 6 months. 2 very important things now we need to talk about. Any compiler, whether CUDA or non-CUDA, has 2 pieces. Okay. The front end, okay. Most probably you have guessed the back end. We can all guess that what is here is your high-level language code, CUDA in our case. And what is here is the binary or executable or the binary. Okay. Now, what is here? First of all, why did they design all the compilers that way? For 2 reasons. The first is the compiler is a pretty complicated piece of software, so you better cut it into pieces. This is one. The second thing is, if you have front end is language dependent, back end is machine dependent. So if you have 5 front ends and 3 back ends, you can have 15 different compilers. In condition that they have to be able to talk the same language here. So the output of this must be able to be some in traditional compilers. What is there is an intermediate representation, IR. In GPUs, which means, let's use now the GPU stuff. So we have CUDA here. What is output is the CUDA binary, QBin. Okay. This is called the PTX. It can be thought of as an intermediate presentation. However, the intermediate presentation for traditional languages is not really very close to the assembly. but the PTX is almost one-to-one corresponding to the assembly of the GPU. The assembly of the GPU is called SASS. Nobody knows what this stands for. Try to Google it and you'll find everybody is trying to make up any acronym for this, and computer scientists are quite good when it comes to these things. But the reality, it's called really, its name is historical a little bit, shader assembly. Because the shading and the GPU, it used to be GPU, so basically shading and all of that stuff, but this is how it is. Okay, but the PTX is a one-to-one presentation of this. QBin is the binary presentation of that assembly. Okay, you can, with some switches in NVCC, generate the PTX version of your code and open it with a text file. You can generate the QBin alone because NVCC under the hood generates the QBin for the CUDA part. The traditional E and F binary for the traditional CPU part, and then it will combine both for you. But you can generate this alone, and there are tools actually to disassemble this back to the assembly. Okay. Now, the problem when NVIDIA started making GPUs, starting from Tesla until Ampere, is that we don't have 100% backward compatibility. This is a problem. Usually, companies like Intel in the x86 needs to have backward compatibility for economical, not technological reasons. If you have a piece of software compiled in 1981, it has to work on the i9 today. Okay. Here it's not the case. So this makes this situation a little bit more complicated. Why? Because you can tell the front end, I want from you to generate the PTX from that code to generate the PTX for a Kepler architecture, or a Maxwell architecture, or a Turing or Ampere. Okay. This is the minus arc. So in the switches and VCC minus arc equal, and I will tell you how to specify this architecture. It's not really written in English like Kepler, Tesla. There is in special notation. Then you tell the back end to generate the binary of a specific implementation. What do I mean by this? When you buy a car, you can say, I want to get a Toyota Corolla. This is the architecture, Kepler, Tesla, but you can say, I want it to be LX, fully loaded, and so on. You have in Intel something called Coffee Lake architecture. That Coffee Lake, when it reaches the market, it will be called i3, i5, i7, i9. So here you can say, I want Volta architecture, but I want it to be V100 GeForce 1080 or 2080 and all of that stuff, because going from this to this, it has to take into account how many SMs, how big is the cache, and so to be a little bit here, from here to here, it will take into account the big features. It has dynamic parallelism, it has blah, blah, blah. Here, from here to here, it will take into account the actual sizes. So for example, here it will take into account that you have a level 2 cache. But from here to here, it will take into account how big is that level 2. Okay. What is quite interesting also is because backward compatibility is not guaranteed, then NVIDIA allows us to have something called fat binary. What does it mean, fat binary? You can tell the front end and the back end, I want from you to generate the PTX for the Kepler, the Maxwell, the Ampere, the Volta, and the Turing. So it will generate PTX and binaries for all of them. It usually removes the PTX. At the end, it will keep the binary for all of them. And then it will add a small piece automatically of software that when you run your executable, it will sense which GPU we have from this, and it will pick the right one. This is what's called FAT, because it has several executables in it. Sometimes you can also tell NVCC not only put all of these binaries, but also keep the PTX. what will we gain from keeping the PTX? To make your program future-proof, which means if you run it on a GPU that didn't yet exist, for Lovelace, for example, or Hopper, then in that case, if that small piece of software that the compiler will put on the top finds that this GPU is not one of the ones that we have the binary for it, it will take the PTX and it will do JIT compilation, just-in-time compilation on the spot. In that case, it will be a little bit slower at the beginning, and then it will continue. I mean, similar to when you go from bytecode to, all of these junk languages that are doing this thing. Basically, this is what we have here. The minus arc, minus code, front end, back end. So how to write to tell the front end that I want Kepler or Maxwell or Pascal, and how to say to tell the back end I want GeForce 2080 or Quadro Pro FX and so on. We will not tell. We are using something called SM underscore and two numbers. This is communicated to the back end. X is the GPU generation number, Y is the version within that generation. These two numbers together, we have given them another nickname before. We call them the compute capability. Okay. As we said, GPU application is not guaranteed across different generations. So a CUDA application that has been compiled for Fermi is already deprecated anyway. Will very likely not run on Kepler, which is deprecated also. So basically, you can run them in the museum somewhere. This is why NVCC relies on these two stages compilation for that. These are basically what you use with minus arc and minus code. If you use minus arc here, you can make the code to be anything higher, but not lower, but not higher. If you don't use any of these at all, like what you have done in lab 1, the default is usually this. So you have been compiling for Maxwell. Maxwell, by the way, was made for portable devices, so it was not very strong one. It didn't even have double precision floating point. Okay. So we have until now, they expect that SM90 will be Lovelace, but it's not yet there. It will be actually quite informative. I think next week or something, there is a GTC conference, and the CEO of NVIDIA will give the keynote. The GTC is organized by NVIDIA, and I think the registration is free and the whole thing is online. So maybe if you want, I can send the link. I mentioned earlier that I will send you the link of something else. So what was that something else? So I can send everything at once. There is something that. Oh yeah, the talk of the top 500. Yes. So can somebody please email me this after this lecture, because I will keep forgetting. I know myself quite well. Keep in mind with all of this, Fermi and Kepler are deprecated from CUDA. So Fermi, starting from CUDA 9, is no longer there, not supported. From 11, Kepler is no longer there. So basically, we are talking about these folks. Tesla with SM20, and it's already fully non-supported now. And we have CUDA 10.4. So you may use Kepler if you want, but we no longer have Kepler GPUs anywhere, CUDA cluster. Okay. Maxwell will be deprecated from CUDA 12 onwards. So after CUDA 12, we will start from here. You cannot use anything of this. So the default will likely be 60 after that. By the way, one thing is important. Don't assume that as we go down, these are more powerful than this. Turing is weaker than Volta because Turing is made for portable devices. In the same way that Maxwell is actually the same strength as Pascal, but for portable devices. So just small rules of thumb here. you should always compile only one -arc flag that matches your most used GPU. Because if you have several -arc, the code generation will be a little bit slower when you start after that, because then it will have to check which GPU and so on. But this is in case you know that you will always run for that specific thing. So you can use actually, if you want, CUDA get device property to know which CUDA cluster you will be running your lab or project on, and then use the corresponding -arc and -code with them, using that table in the previous slide. If you only mention -code, which means you don't use -arc, then things will be even slower, because then you are telling it to use JIT compilation. So basically, it means that it will keep in the binary only the PTX, and then once you start executing it, will translate the PTX to binary, and then, which is a little bit slower. At the start, it is the execution itself will not be slower. Okay, the JIT looks like this. You know the JIT, like those of you who know about Java virtual machine and all of that stuff. And you people usually use this if you are writing a code that will go to people and you don't know which GPU those people will have. So in that case, instead of having very fat binary to compile with everything, just keep it with a PTX and then it will. Okay, so now we know the PTX, the SAS, the QBin. Intermediate presentation, one-on-one correspondence with the assembly, the binary version of the assembly. So the fat binary looks like this. NVCC, this is your code, -arc, compute 30, and then -code, compute 30, SM30, SM35, for example. This means that the executable generated will have the executable for these two. But also, since there is a compute, not SM here, it means you are telling it to keep also the PTX. So it will be future proof. Okay. This is basically what's happening. At runtime, the CUDA driver will select the most appropriate translation when the device function is launched. Till now, we have been using one arc. You can even use several arcs. Of course, it has to be one line, so we're using the backslash. Minus generate dash code or minus gen code. This is a combination of arc and code at the same time, if you want to put them. So here we are using several virtual machines. Here, actually, the binary generated will be pretty fat, big, basically. Okay. Now, you will not need all of these for the labs or the project, but this is good to know that they exist. But now here, there is something that you may need in the lab, or if you use with NVCC --PTX assembly -option verbose, this means it will print the shared memory registers and other resources usage by your code. Statically, of course, because there is no execution. If you want to see the code QBin, then the NVCC -QBin will generate a file .QBin. This is the binary version of only the GPU part. You may say, okay, what is the importance of this? I mean, it's binary. Well, there are something very similar to this assembler that we had for the CPU, but for this, that we can allow you to go back and see what is going on. And there are some tools actually that can map this to the source code. So you can see. Now, if you want to see the PTX, this is a text file, and NVCC -PTX will generate the PTX version. If you use this, oops. What is going on? If you use the one that will give you the resources, it will print on the screen several things that are not very understandable. So in order to decipher it, this is what will be generated on the screen for your code. This is the global memory. easy to understand how much global memory your code is using. Statically. Shared memory, the CUDA shared memories that you have used, just in case. LMEM, the local memory. You remember the local memory, which is basically if it doesn't fit into a register. The larger that number, the poorer the quality of your code will be. Constant memory, but this is not the constant memory that we know only, because it will just print this and then it will say constant memory 0. These are the kernel arguments. They are passed through the constant memory also. Constant memory 1, these are some variables related to your kernel. That's not written by you. So it's not the kernel, something for the control between the runtime and constant memory, user-defined constant objects. This is basically what you want. This is if you want to put something in the constant memory. 14 and 16 are for compiler-generated constants. Remember that the compiler is not a direct one-to-one presentation of your code. It may add several things. It's like in x86, all this extra code of managing the stack was not in your original code. It is basically something to make the code behave in the way that you expect. Okay, NVProf. That NVProf and the visual profiler of it will be deprecated in the next CUDA release. So after that, you have to use NSite. I put a link to NSite at the last slide here. But NVProf so far, and for this semester, you can use it in the projects or the lab. It is quite useful because it's just command line. Okay. So NVProf with its own argument, you are telling NVProf what do you want to profile, and then your binary with its data or its arguments if needed. Suppose that you want to profile only part of your code, a specific kernel from it. Then inside your code, you need to include CUDA_profiler API beside CUDA.h, of course. And then around the kernel that you want, or around calling the kernel from the host, or if you want to profile not only the kernel, if you want to profile the CUDA memcpy, anything, CUDA profiler start, CUDA profiler stop, and then you compile. Okay, and then you can, after you compile, so you have the binary NVProf. Don't forget to do this, because even when you use this, it can start profiling from the very beginning. So you have to tell the profiler, do not profile anything. So starting from the beginning, from start is off, and then this. Then it will give you a lot of useful statistics about that part of your code. If you don't use those, it will profile everything. Okay, what is everything? If you just use NVProf without anything at all, it will give you the summary mode, the default. Okay, so it will tell you, for example, that the CUDA memcpy host to device has been called twice. The minimum time is this, the maximum is this, the average is that. The one that is called one time, add vector, this is like the kernel that you added, and this is the device to host. Here, it will tell you the amount of the percentage it took. So as you can see, the CUDA memcpy alone took 70+% of the total execution time. This will give you this and this. This is the kernel. Also, you can see the amount of time taken by each API alone. The CUDA memcpy, CUDA Baroque, CUDA free. Those, the things that start with CU is even a lower level APIs than the stuff that will start with CUDA. And we didn't want to go all that way down. So all of these are happening under the hood. When you start launching a kernel, there are many control APIs under the hood that set the stage and all of that stuff related. It's very similar to when you start executing any binary for a real machine. There are many things under the hood. It has to set the virtual address space, adjust the stacks, the text. So something very similar here, but it tells you, it is very good to know how long does it take, what happens under the hood, because all of what happens under the hood is not your fault. Okay, so you need, here in that case, you will be able to see what is in your fault. Okay. And those are the API calls only, not your code. Your code is this. All right. There is something called the trace mode. Dash print GPU trace. In that case, it will not show you the minimum, maximum, and average for kernel launch. It will give you each one individually. If you are calling that kernel several times with all the grid size, the block size, and how much, and all of that stuff. Okay. You can use both. You want to see the GPU trace for everyone, and also you want to see the APIs that we saw, so it will combine both in that case. Okay. This is very important thing now, because this part, here you have to pick the device. Because if you have several devices attached, as we will see in multi-GPU system, every device will be numbered, starting from 0. So if you have 2 GPUs, one is 0, one is 1, you have to specify the device, and then you have to specify the events. This is a comma listed thing. Here is the place where you can know how much you have in branch divergence, level 1 cache miss, level 2 cache hits, these things. Actually, if you use NVCC double-dash events all, it will print a very long list about all the events that it can measure. So you can see the stuff. Okay. How much time at least one warp is active, because if sometimes no warp is active, it means all the warps are waiting for the global memory. Do you remember there was one quick exercise we did here? How many warps do we need to keep the SM always working? So this means that you may need to increase, for example, the number. There is something else called matrix. The matrix is different than the event. What does this mean? An event is something like branch divergence. This is an event. A metric is how many loads, how many stores. This is not an event. A load is an event. Is a metric. But a cache miss is an event. And you can, if you also use double-dash metrics, all it will give you a long list. And you can get a peace of mind and let it measure all the metrics and all the events and pick whatever you want. But you will get really huge list. Okay, CUDA mem check. This is a different tool. Okay, capable of detecting and attributing out of bound and misaligned memory access. We'll talk about alignment in CUDA Advanced Part 2. Reporting hardware exception and counter. For example, if a kernel will fail to launch, if you try to CUDA malloc and you run out of memory, sometimes you may have a CUDA malloc with a space or with a size much smaller than the global memory, and still it fails. Why? Because some other people are using the GPU as you. Everybody is near the submission, so everybody is working on this thing. See, you guys are the new generation who is always working on the labs and the project only near the deadline. But the older generation, like myself, we were also working on the labs and the project near the deadline also. But I have to act as if I'm the professor and I have to give you some wisdom, but I never did this before. The only thing is that during my time, the technology was much less than this. We were kind of hiding. Nobody will know. Here now everything is online. And we didn't have Stack Overflow. So this made us a little bit better than you, because we have to work our mind a little bit. We cannot Google anything. So until I finished my PhD, Google didn't exist, Skype didn't exist, YouTube didn't exist, Facebook didn't exist. So I don't know where I was wasting my time during that. Race check, report shared memory data access hazards. Remember, no coherence, nothing, so it's up to you. So here it will detect this in case more than one thread. And this can happen either in shared memory, if two threads in the same block are trying to update the same element at the same time. This is a problem, but it is your problem because the system will not. Init check reports cases where the GPU performed uninitialized access to global memory. This is a very good thing. In CPU, we know this, you are using something without initializing it. Sync check cases where the application is attempting invalid use of synchronization primitive. When the synchronization is invalid. Synchronization is a synchronization. Which under which circumstances a synchronization can be actually invalid.
Synchronization in the branch.
This is one thing. This will cause a deadlock actually, because they are different synchronization. The if and else is not the same sync third. And if you try to synchronize across blocks, this is not also allowed. How do you know this? All of these have to use CUDA memcheck. All of these are embedded within this. So you have to use CUDA memcheck and then double dash tool and then one of these names and then your binary with the arguments. Then it will tell you whether there is a problem or not. So it is, but you need to compile with -g. -g is very similar to minus lower g in GCC, if you know, which means it will keep debugging information there, because then the CUDA memcheck can tell you, okay, you have a problem in this line. Otherwise, it will not be able to go back to the high level. Okay, this is basically one of these things. All of these will be deprecated starting next year. CUDA is usually updated once every. I mean, we can make quick calculations. We are at CUDA 12, and CUDA was born in 2006. So this means they are updating CUDA once every 1.5 years. However, this every 1.5 years is the release for the new full CUDA, but things are deprecated in the middle. So every 6 months, you need to take a look. After they are deprecating NVProf and all of that stuff, the end site system is better, and it is GUI, by the way, so you can see the stuff instead of having. And they have also a command line interface for those who prefer a CLI. They are free, so you can download this thing. But if you are going to use them, they are already installed on the SIMs, so you can just use them. But I'm not sure. For sure, you can use the CLI, the command line version. But to use the GUI, I think you need to SSH with -X to have the X video to be able to open something GUI while you are at home. I believe so. I mean, okay. Any questions about this tool? That was just a quick. This slide is already on the course website in the commands part next to today's lecture. Okay. I think we will start the part 2 next time because we don't have enough time to do this now. Next week, hopefully now you have a lot of tools in your arsenal for lab 2 and for the projects. I hope you can start the projects as soon as you can. I send an announcement that December 1st is the deadline to send us everything for 2 reasons. First, this will give you some time to prepare for the final. I mean, you need to study also. There is a final exam, right? And the second thing is that our grader also has his final exam. So in order for him to you know, because I will ask him to run all your code and tell me whether it works or you are really making up the numbers. Of course, I mean, do you think, do you have the slightest doubt that I don't trust you? If you were a professor, will you trust the students, yes or no? And be frank in this. Okay, then you know now why the grader will have a lot of, but I will be looking at the reports. And if I find, we'll be very generous with that grade, so don't worry. But if I find that you did the really good job, I may email you back at the end of the semester or after the semester to send it for publications. But of course, we'll have to make some restructuring, this different format, if the work is really good. Okay, thank you so much. Let me stop the recording here.